welcome. Here we are again. Let's see how this goes. Oh, this is so much better. Still have dropped frames and buffering, but I think this is a lot better. Let me see. What does it sound like? Buffering, but I think there we go. That's a lot better. All right, let's go ahead and start working. All right, so we're starting to, we're going to break the 80% acceptance rate. So we're starting to get into slightly harder problems, but these are all relatively easy questions. I could try a hard question, but I kind of would prefer to just keep doing easy problems for a while. I can go through a few thousand easy questions before I have to do any hard ones. At some point, though, that's all that's going to be left is hard ones. All right. You want to water N plants in your garden with a watering can. The plants are arranged in a row and are labeled from 0 to N-1 from left to right, where the ith plant is located at x equals I. There's a river at x equals -1 that you can refill your watering can at. Each plant needs a specific amount of water. Water plants the following way. Water them left to right, watering the plant. If you do not have enough water to completely water the next plant, return to the river to refill the watering can. Cannot refill the watering can earlier. Okay, initially at the river, it takes 1 step to move 1 unit on the x-axis. 0 index integer array of plants. Plants divides the amount of water ith plant needs. Integer capacitor represents watering capacitor. Turn the number of steps needed to water all the plants. Plants 2, 2, 3, 3. Capacity is 5. So you can do the first 2. Then you got to move back. Okay. 1 step. 1 step. Move back 2 steps. 1, 2, 3, 4. You gotta do 1, 2, 3 to come back. 3 steps. Then you have to go back again. Oh man, this is an interesting question. I wonder if there's a way to optimize this. Capacity could be, let's think, like 1 billion plants. Oh man, there's 1 million plants. Whoa. Oh no. Is it only 1,000 plants? Okay. But the plants could be up to 1 million, and the capacity could be 1 billion. I think there's a way to do this that's more efficient. I gotta think about it a little bit. Yeah, interesting question. Okay. All right. What I'm gonna say is, let's think about it for a minute. If there's a way I can kind of, no, obviously I could simulate this, and it could probably be relatively fast, but I think there's a faster way to do it. So, all right, I can figure out how far I go left to right based on the capacity. And once I've reached the capacity, exceeded the capacity, then I know I need to make the return back. So I can count the number of steps until the capacity is exceeded, and then basically double those steps. So it would be 2 steps, and then 2 steps to come back. Oh, triple it, right? So you go 1, 2, 3 to come back, triple the number of steps that I've made up to that point. And then I guess you just keep repeating. So that would be linear time. Let me see if that's correct here. So let me just double check. So it's 1 step, 1 step. And I actually don't take this step, this next one. So I walk back twice. Then I walk back again, but I do have to make 1 more step to enter. Okay. So it'd be triple plus 1. It's 2x plus 1, basically. Well, watering it would be 1 walk back to plant, 2, 3 steps of water it. And then I've got also important, it's not the distance from the last position that I need to be concerned about, but the total distance. So this is position 2, which is going to be 3 steps. So I plus 1 is the number of steps. So it's going to be here to here is 1, 2, 3 to get back here, 3x. And then the next position, again is going to be 1, 2, 1, 2 to get back to that position. Okay. Maybe that's the way to do it. You just double the index that you're at when it runs out. And then that brings you back 3, 6, double that to get here. And then you go to the next position. Okay, I think I know what to do. Let me think about it. Let me go through it again. So it's going to be, you move left to right until you run out of capacity, and you save that spot. And just before that position, you double that index and add it to the total. Then you continue processing from the position that you're at with the new capacity, the full capacity. And then you keep going some amount until again you stop. Again, wherever let's say you stopped here, oops. So some stopping index just before that, you're going to double that, add it to the total, and then to process you would add 1. So you do have to add, so you have to add each step forward as well. Okay, interesting. Okay, let's try this. Let's see if I understand. So we're gonna have a double, I think. All right. Result 0. Return the result. And we're gonna say int I is 0, I is less than my instance size. Okay, so I don't necessarily need to do it this way. We're gonna say int current. First, we're gonna scroll forward. Okay, also have to handle if I go off the edge. We'll come back to that. And current plus plants of j, or just say current is less than capacity. No. We'll come back to this. So we're gonna say constant val is plants of I. Say if current is less than value, then we're gonna break. Otherwise, when it's equal to this value. So take a certain number of steps and increment the result. Take a certain number of steps until current is less than the value. Okay, that's J. Now let me actually put J here so I can access J. Now, once we're at a point where could also just current is greater than or equal to value. Okay. So we move J forward while we can subtract, and we count each step. And then we hit a point where then we hit a point where either J is off the edge or our capacity, we can't water that plant. Okay. So then we've got to move all the way back, all the way forward. So if j is greater than or equal to plants.size, then we're done. Then we're done. Otherwise, we're going to set I equal to j, and that's going to be the next position. We're going to increment the result. Oh no, we don't have to increment the result. We are going to increment the result, excuse me. And we're going to take result plus equals I minus 1 times 2. I actually don't need that because it's 1 indexed, 0 indexed. So this actually doesn't matter. So there's going to be a plus 1 minus 1 thing going on there. So if we stop at index 3, we passed 0, 1, 2. When we stop at index 3, it means we have to go all the way back from 0, 1, 2 to the left 3 positions and then back again, just to get to the position 2, 0 indexed at 2, and then move. We have to plus 1 more to move over. Yeah. I think this is it. Let's try this. Something like this. Hopefully it doesn't TLE and hopefully it doesn't run into unexpected issues. Okay, so there's an issue. Yeah, this is, the logic is kind of tricky here. Okay, so current has to be set to capacity. I forgot about that. That's important. There's a subtlety here. The values for plants should be less than capacity. Yeah, this is a constraint that they give you. I was gonna say this, you could run into issues. 17 should be 14. Okay. So here, what does my loop do? Let's print ij and result. I j and result. Okay. Then maybe current as well. I don't know if that's that helpful. We'll come back to that. Maybe it's helpful. Just put that there. This is probably an off by 1 error of some kind. Okay. So 0, 0, result is 1. Okay, I need to see what current is. Debug. I'm not sure what happened here. Oh, that's what's wrong. Okay, got it. It's one of these things that are wrong. Potentially other things that are wrong. Okay, so still the wrong answer though. Okay. So 0, 0, current is 0, should stop. That might be another issue. Initially starts at capacity. Okay, that's another issue. Okay. All right. So we get down to 1. So I is 2, j is 2. It's kind of weak. Actually, these are always going to be equal to each other. We have, yeah, that's the first time it stops, and it stops again here. We have 15 instead of, or 16 instead of 14. Hmm. 7. 1, 2, 3. 2, 3, and then 1, 2. That should be 7. Yeah. It's gonna be 1, 2. Stop here. Don't go. Back 2. Back 2 again, and then jump. So it's gonna be 3 plus 2 plus 2 to get to this point. Then from here, it should be 1. Oh, that's probably why. It would be 1, 2. Yeah, that's part of the issue. Okay. Let me get rid of this part. This is probably wrong. That's kind of subtle. That's probably the issue. Yeah. Yeah, not the easiest to kind of think through, but I think that's the problem, is that it already, the next cycle already accounts for stepping through. Okay. Fairly simple. Let me see. This actually can just be I think, by the way. This could be I the whole way through. Yeah, that could just be I the whole way through, I think. Let's see. Yeah, all right, let me try some other test cases, and then we'll I have to increase the capacity, though, for this. All right, let's try this. These maybe aren't the best test cases. Maybe I could do better. Let me do like only digits or something. Or something more like, I'm not sure what the word is, what the expression is. Something, it's like easier to work with, I suppose. Something that, it's a little, tests a little bit more than like, I'm not sure what the word expression is. Like, these other test cases are a little bit too small because the range of values are too large, and so it matters more about like the ones that are nearby the capacity. Whereas these ones, it's a different kind of distribution. I'm not really sure how to express that succinctly or easily, but this looks like it's probably correct. I'm going to go for it, see what I get. This is hopefully linear time. Yeah, there we go. Pretty good. The memory is terrible, though. What the heck? What happened with the memory? This doesn't use any extra memory. This is just like, what? What happened? There's like 2 extra integers. What's going on? What in the world? Great job. Thank you. What's up, Piyush? How's it going? Welcome, welcome. Howdy. Thank you. Okay, there we go. That's a little bit better. All right, let's keep going. Yeah, maybe I could have come up with a better way to explain that, but that wasn't too bad. That was okay. Design a stack with increment operation. Design a stack that supports increment operations on its elements. Implement the custom stack class. Custom stack int max size. initializes the object with max size, which is the maximum number of elements in the stack. Void push index adds x to the top of the stack. If the stack has not reached the max size, it pops and returns the top of the stack. -1 if the stack is empty. Void int k, int val increments the bottom k elements of the stack by val. If there are less than k elements in the stack, increment all the elements in the stack. Okay, so we have custom stack, push, pop, and increment. Bottom k elements by val. If there are less than k elements in the stack, increment all the elements in the stack. Oh, that's interesting. I mean, there's a way to do this. It's maybe not the best, but yeah, okay. We can, it's kind of a cheeky way of doing this. 1,000 calls. All right. So we're gonna use 2 vectors. Oh, it has a max size too. Oh man. Oh wow. Okay. Can we change the max size? If we can't change the max size, this is even easier. Okay. So okay. So I think we do vectors. So int, it's gonna be increment, and it's gonna be like val and increment. Val and increment. Yeah. Okay. Oh, it's val and increment. And they're both gonna be max size. We're gonna say size. Size and increment size. Okay. And we're gonna have integers, val index and index. All right. And when we push, we're going to, excuse me, I did this wrong. Oops. This should be private. I think they usually put the private after. I've seen that. I kind of like putting the private stuff first. I kind of prefer to put the private things up here. But I've seen that where they put the private things afterwards. I'm not sure if that's good. Okay, so these should be, yeah, that's okay, got it. These should just be initialized as empty. And now we're gonna do, okay, there we go. That looks, so I wonder, some kind of custom allocator might be a good idea here, but for now, we'll just keep it simple. Okay, so push and, oh yeah. I'm gonna do this here. Even though, I don't know if I can do, I don't know if this, I think this works, but I'm gonna reset them to 0 anyway. Okay, so now push is gonna, val of val index is going to be set to x, and we're going to increment val index. Okay, and also I think the increment index also is, yeah, this will be set to 0. Okay, so you can kind of see what's going to happen here. So basically we just managed 2 stacks. So when I pop, I'm going to decrement the val index and decrement the inc index. This also will be set to 0. And this probably should be set to 0. Okay, but actually they want to get the value, so constant result, or not constant result, is started with 0. We're going to say val result, actually do it this way. Val index. It really is going to be a val index plus inc index. So the idea is that when I pop the ink index, it's going to be propagated downwards. Yeah, which I probably should have explained. So we're going to say ink index is greater than 0, then ink of ink index plus equals increment, current increment. So set this to 0, decrement, pop it, and then we're going to set the propagate down, and then result is going to be plus this increment index, or current increment. Something like this. It's maybe a little bit convoluted the way I've shown that, but something like this. And then when we increment, this becomes as simple as the k element, so k minus 1, we can do ink of ink, or just ink of k minus 1 is equal to value. Less than k elements, increment all elements in the stack. Okay. And increment them by value. Okay. So plus equals value. And we would say, I guess if k is greater than value, so we could take a look at the increment index. The increment index should match the value index. So basically so k minus 1 would be an index instead of the number of values. So if we had 3, the index 2. Okay. So basically, just make this the minimum of these two. And then use k. We could do something like this. Okay, so if k is too large, then we're just going to push it right in the top of the stack. Something like this, I think, could work. I'm going to give this a shot, see how it goes. I didn't really explain. I probably should explain it a little bit better. Runtime error, okay. Oops. All right, hold on. Oh, I did this wrong. Oh wait. Oh, I see. I made a mistake here. If it's empty, okay, you could pop if it's empty. I have to come back to that. That's a mistake on my part. There's also this could be negative. No, I don't think k is negative. Yeah, k is negative. Excuse me, k is never negative. Also, it doesn't say if can you push. If I push and it exceeds the limit, stack has not reached the max size. Okay, so I do have to check both those things. All right. Couple issues there. If valid index is less than size, yeah. So it should probably be vowels instead of vowel. And then the other issue is if I pop if vowel index is less than 0. Just return -1, skip, don't do anything beyond that. I think that's handles those cases. Let's find out. No, it does not. Okay. I need to debug, I think. Oh, it's the increment actually. Okay. Huh. Really? Oh, what is happening here? It's going good. You preparing for any interviews or just for fun? It's kind of a mixture of the two. It's not really preparing for interviews exactly. Whoops. I was thinking about doing coaching. Was one of the ideas that I had. If folks are interested in that, but actually, I was thinking there's something else I might want to do. So it's kind of a mixture of for fun, but also the other ideas that I have. All right. So index 3, and what was the size? What was the size? Does it say custom stack 3? Oh, the first element's the okay. So 0, 1, 2, 3. Yeah, so 3 is out of bounds. All right. Where is increment? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Where is increment 5, 100? What? Oh. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Oh, okay, so it's 5, 100. Okay. I see. 3. Oh, it should be 2, actually. I got 3 there. Oh, because the increment index could have already be off. Oh, I see. If it's a full stack, then yeah, it's interesting. Oh, okay. So actually, the pop should decrement first, I think. Oops. That's kind of a subtle thing, but the pop should decrement first. Okay. Basically, this is going to be pointing to an empty element each time. So I would want to decrement down to an element and then remove it. Oh, okay, interesting. All right. Yeah. Right, and then cascade down. Okay. All right. So that means this also should have a -1. If it's empty, then we just return. Okay. Interesting. Or excuse me, if it's less than 0, I did that wrong. All right. What's up, Anuj? Hope your day's going well. Welcome, welcome. Oh, howdy. Okay, there we go. I think I'm just gonna go for it. I probably shouldn't, but I think I'm gonna go for it. Yeah, this code ended up being a lot more complex than I was expecting. Simple idea. I'm gonna go for it. There's a high chance there's a mistake in here somewhere. Oh, nope, we're right. Hey, got there. Okay, sweet. This isn't too bad. The push isn't too bad. The pop is tricky, as I kind of explained. Cascade, remembering to cascade, remembering that the indices are going to be pointing to an empty spot, so I need to actually decrement them before I can, and then decrement and clear that spot. And then this probably could be coded a little bit better, so it's a little more clear what's happening. And then the increment also is additive, and I've got to keep track of how many elements we're processing, like how many elements are in the stack. And then also not try to increment. Basically, if I try to increment on an empty stack, handle that appropriately. Interesting. So it worked. It's pretty good. Let me see if I can get a couple things I want to see here. So only 8 milliseconds is not what I was expecting. I was kind of hoping for a slightly better time bounds. And let me see if, okay. Oh, 100%. Okay, we're fine. All right, let's read what the AI thinks. Correct and efficiently uses the lazy propagation technique to achieve constant time complexity for all operations. Lazy propagation, 2 parallel arrays, stores actual values, stores pending increments, key logic. Okay, explains all that. Micro optimizations, refinements, highly optimized, minor suggestions. Okay. Explicitly clear increment on pop, decrement, logically remove the element if you ever reuse the slot. Having garbage could be risky if logic changes. Current code after decrementing, which correctly clears the slot pop. This is correct. Okay. Reallocation in constructor. Initialize the default constructor inside the constructor body. Slightly more efficient. Use initialize the list or resize directly to avoid double allocation. Oh, I should use resize. Okay. Or what happens here when I use the initialize list? I like that. Actually, I like the initializer list idea. I should be doing it. That's a lot cleaner. Not cleaner, but it's like a better syntax, I think. Yeah, I think that's better. I should do that for sure. Size 0. Pink size 0. And then val index 0. Pink index 0. Let me see if I did this correctly. I don't use initializer list syntax very often, and I should use it pretty much all the time. Okay, direct construction. All right. Before the constructor body executes. Allocated once, initialized to 0, single step, no default construction occurs. Default construction, default constructed, temporary creation, okay. Copy move assignment. Okay. Got it. Unnecessary allocation and initialization for the temporary vector, which is then moved. Oh, okay. Oh, very interesting. Okay. Okay, let's see if there's a difference between those two. So that was slightly inefficient, actually. Do it that way. I think this is all right. I kind of like this style. Like something like this, I guess. Yeah, this sort of approach. Maybe this isn't perfect, but this is reasonable. I could even do this. Like keep them all like so. I kind of like this style. Okay. Default constructor vectors in the member declaration, and then resize them in the constructor body. You incur a double initialization penalty that makes it slower than both the initializer list and the assignment approaches. Oh. Constructor body allocates memory for size elements and value initializes them. One allocation went past to zero initialized memory. Oh man. Whoa. Okay, initialize a list. Construct directly. One allocation, one initialization. Default construct empty. Create temporary vector. Move temporary to member. One for temporary, one for temporary. Fast, move is cheap, attempt creation overhead exists. Okay, one allocation, one initializer, still pretty fast, okay. Resize, default construct, empty, resize member allocate, slower function call overhead plus potentially less optimization than direct construction. Okay. Similar to the assignment approach, soft and slower. I thought that would be faster, okay. Method call on an existing object, whereas the initializer list constructs the object directly. Interesting. Sometimes optimized constructor initializer lists better than method calls inside the body, although for stood vector the difference is often minimal. Stick with the initializer list. Idiomatic clear is theoretically most efficient. Oh, okay. There you go. Go figure. Sir, I also use Leo AI. It's great. Yeah, it's a good one. What's up, Spy Gamers? Howdy, howdy. That's great. Good luck. And with that, have to take off. Okay, take care, Push. I appreciate you coming by and saying hello. And those of you who like the stream, don't forget to give it a, subscribe and give it a like. Mostly because the way the algorithms work, if you're not subscribed, then it's very unlikely that you'll see the videos again when I'm streaming. I think. I could be wrong. 3 milliseconds, okay. That's not too bad. I'm not sure if my minor optimization here really made much of a difference. Don't know. So that's one optimization. What were the other? Yeah, 100%. Okay, that's pretty good. Oh, shoot. Wait, no. Didn't mean to do that. Cancel. Stop. I didn't mean to click that. Okay, we'll leave it there. What were the other optimizations that it suggested? Okay. So stood vector reallocation. Const where possible. Okay. Local const variable inside functions can sometimes aid compiler optimizations. Okay. Redundant zeroing and push. Excuse me, in push you do inc x equals 0. Since ink is initialized to all zeros and you cleared upon pop, this is technically redundant unless a slot was popped and is now being reused. Since you reuse slots using indices rather than push pop back, this zeroing is necessary and correct. What? Wait, what? Ink equals 0 when I push. Pop. Push. Oh yeah. No, this is, yeah, it's necessary. Yeah. No, it's definitely necessary. I'm reusing the slots, so yeah. Okay. So this is that's definitely important. Clean state for use slot, exactly. So I think that's my push is the same. Whoops. Oh, shoot. Hopefully you didn't just lose sight of that. Okay. Yeah. Let me see here. So maybe actually it should just be one index instead of increment index and val index. And it's always the same, right? Actually, I only need one of these. Correct. Okay. Yeah, I only need one index, actually. Thinking about it. Now that we're reviewing this here. Oops. Do some refactoring. Okay. Right, interesting. See if that's still correct. Okay. Let's try it. Let me actually see what it thinks about my modified version here. Or some of the other, whoops. Ideas. Temporary creation, copy, move. Move assignment. Temporary vector. Oh wait, do I already? Yeah, I already went through that. Okay. What were the other optimizations? Okay. Clear the slot, propagate increment element below. Oh yeah, the min sum -1 could have been slightly moved out of there. Yeah, that's fine. Rename parameter with shadowing. Okay. I didn't even notice that before. Code is optimal. All right, pretty good. So what? What do you think? I think I got a little bit confused because I modified the excellent optimization. Okay. Always identical. Yeah. Okay. Any other micro optimizations you might see? That's probably it for this question, I think. It's pretty good. Pretty simple. Yeah, a couple of slight things that I missed though. This is also kind of subtle. I'm putting the -1 on the outside there. Didn't get 0 milliseconds for some reason. Oh, hold on. Oh, fine. Would like to get 0 milliseconds again though, if I could. Nice. Raw pointers in pushpop. Direct point arithmetic to eliminate bounds overhead. It's usually optimized. Pointers once in the constructor. Merge single array of pairs. Cache locality. Oh. Stood min. Optimize better than stood min. Using @exit to override the runtime. No. That's so funny. No. That's cheating. That's cheating. That's so funny. No. Cache locality and point arithmetic. Okay. So this is stood pair. Okay. So we still got 100%, but yeah, actually stood pair is better. Didn't think about that. So it's going to be, what do I call this? Stack. C stack. For custom stack or special stack. S stack. Call it S stack. Okay. Interesting. Okay. Let's try this. So push is an S stack of index equals 0 or x0. Okay. Okay. Something like this so far. This apparently gets optimized a little bit better. Let's try this. I'm gonna go for it. So better cache locality. I didn't think about that. That's a good call. Oh, that's a lot slower. Uh-oh. Uh-oh. Maybe it just didn't get warmed up. I don't know. Oh boy. Huh. I think this is a lot slower. Huh. Hmm. I think actually may have been better. Use the separate arrays. Think the code appears to be running slower. Slower now. I switch pairs. Could be wrong, but this seems actually a lot slower. Whew. Good. How are we doing here? May have run into some issues here. Hey, what's up? This is a lot better. 1 second. We're back. May have run into some issues here. Okay. Oh, there we go. All right. Boy. Howdy. Howdy. Okay. 1 millisecond. All right. I think this is. Oh yeah. Too. Okay, try again. Oh, I got stuck. Okay. Let's do it this way. Try it this way. Let me submit it one more time. I'm not sure if this is. Oh, that's what I was doing. I was asking. Yeah, I was asking if it's faster or slower now. Oh, 100%. Okay. Oh, it's separate. It's faster here. Increment. Ah. Oh, okay. It's wasting cache bandwidth. Interesting. Okay. I still got the 0 milliseconds, but yeah, it does seem to be slower. Okay, we'll go back to 2. It's optimizations that are actually slower. Golly gee. Golly gee. Huh. Who would have thunk it? Who would have thunk it? Alright, let's see if this still works. Very interesting. Thanks for that analysis. Oh, compile error now. Okay. Oh, I'm midway between various optimizations here. That actually was correct. Removing the other variable was correct. Okay. There was this part that was not correct. Cool. Cool, very cool. All right, I'm gonna submit this one more time. Yeah, I spent a lot of time on this question, but I was curious. There we go, super fast. All right, pretty good, pretty good, pretty good. All right, let's go. Maximum XOR after operations. Zero indexed integer array nums, one operation, select any negative, non-negative integer x and an index I, then update nums of I to be equal to nums I and nums of I XOR x. Well, that's interesting. Note that AND is the bitwise AND operation and XOR is the bitwise XOR operation. Return the maximum possible bitwise XOR of all elements of nums after applying the operation any number of times. Oh, wow. All right. Want the maximum possible bitwise XOR. Okay. Huh. 11 maximum possible bitwise XOR. Don't apply this operation. Take the XOR. The 2's will disappear here. It'll just be the XOR between 1, 3, and 9. Interesting. This might be wrong, by the way, this one. I would guess this is not correct. Let me come back to that in a minute. Non-negative integer x. Index I, updating nums of I to be equal to nums of I and nums of I XOR x. So, okay. Basically, if I XOR nums of I with x, I can clear any bits that I want to clear. And I can flip any bits that I want to flip. But the problem is that nums of I is not going to I can clear any bits I want to clear. I can flip any bits I want to flip, but I won't be able to get bits in nums of I that aren't already there. So the best I could do is clear whatever bits in nums of I that I want to clear. That's the best I could do because of the AND. So, okay, so I can clear bits. All right. However, 1, 2, 3. Oh, it doesn't matter if we eliminate the 2. What we do with the 2 is because there's a bit flip for 3. And 9 has a bit flip as well. So basically, it's just going to be the... Quite frankly, I think you just OR the whole thing. Yeah, you just OR these all together. Also, we crossed the 80% threshold, so we're now in slightly harder than very easy questions. I think it's just the OR of all these. So int result equals 0, return result, or constant x in nums, result, or equals x. I'm gonna go with that. I think that's it. Yeah, I think that's it. Let's do a couple more. Let's add more elements. I think we. Oh, I'm starting to drop frames again. That's not good. It's doing so well too. Let me just check and see that this stream is working. Hey, what's up? Yeah, it looks okay. It's doing so well too. Looks okay. Unfortunately, dropping frames a lot though, but not terrible. All right, I'm gonna go for it here. I think this is it. I think this is correct. Yeah, that's right. Yep, 100%. It's correct. There's not really much to say about that. It's just you just take all the bits that you can get across the input. Okay. Determine color of a chessboard square. You're given coordinates, a string that represents the coordinates. The square of the chessboard below is a chessboard for your reference. Okay. True if the square is white and false if the square is black. Coordinate will always represent a valid chessboard square. The coordinate will always have the first letter and the second number second. A1 false. Square with coordinates A1 is black, so return false. Excuse me. Okay. So this has like kind of an algorithm to it. I think it's basically. Oh man. Hold on a second. This has kind of an algorithm to explain in a moment what that is. It's just I'm dropping a lot for. Oh no, we're okay. Let me refresh something here. So the algorithm is going to be. I think it's oh. Oh, is it working? It's working. Okay. All right. All right. It's fine. Confusing. It looks like it starts off at so you can add them together and then take modulo 2 basically. So 0, well, yeah, subtract a and subtract 1. So it'd be 0, 1, 2, 3, and then 0, 1, 2, 3. So you add them together and you get 0. Mod 2 and get 0. Here's a 1, mod 2 is 1, 2, mod 2 is 0, 1, so on. And then you add similarly in the next direction. So I want to say it's as simple as that. It's just that's going to be the coordinate. First coordinate is, I think, A. And the second coordinate is 1. And just take this mod 2. I'm not sure if there's a better way to do that. Instead of mod 2, I think I can take it and 1. Wrong. Okay. If I take it and 1, it's like inverted, so it's mod 2 is probably better. And 1, if it's odd, gives you 1. Mod 2, if it's odd, it still gives you 1. Oh yeah, no, and 1 is fine. I think and 1 is fine. Yeah, if it's odd, you get a 1. If it's even, you get a 0. Okay, that's correct. That works. but this is not right. So H and 3. Oh, that's why. One of these is a 1, one of these is a 0. I was gonna say, I thought my logic was fine there. Yeah, I think it's that simple. I do think it's that simple. Pretty straightforward kind of a thing. Yeah. Not much more. Is it still buffering? Yeah, it's still kind of buffering. Not ideal, but not the worst. Let me keep going here. So yeah, that's a pretty straightforward solution. Not much more to say about that. All right, maximum frequency, total frequencies of elements. Okay. It's only up to 100. That's not too bad. What do they do? So 1 and 2 have a frequency of 2, which is the maximum frequency. Number of elements. Okay, interesting. So what did I say? It's up to 100. Yeah. All right. So frequency maps. Doing some frequency map manipulation. So first we'll get the frequencies. This is just simple as that. And then sort frequencies. And then, actually, you don't even need to do that. You could just get the maximum. And then we would say int result 0 by 0, I is less than 100, let's get 100. If frequency of I equals max frequency, result plus equals frequency. And that's it. Hopefully this is fast. All right, I'm gonna go for it. I think this is probably correct. The logic here is, fairly straightforward. I think, yep, 100%. Okay, we'll just keep going. That's not that hard to work through, think about. Cells with odd values in matrix, n by n matrix, initialized to all zeros, 2D array indices. R of I, C of I represents a 0 index location to perform some increment operation on the matrix. Okay, interesting. Okay. Each location indices Y do both of I. Increment, all the cells in the row and all the cells in the column. Oh, okay. Wow. All right. M and N and indices return the number of odd valued cells in the matrix after applying the increments to all locations and indices. Huh. Oh. Wow. M, N, indices. Oh, they just give you M and N to start with and then a bunch of indices. Okay. M and N could be 50 indices, 100. Can you solve this in O of n plus m plus indices length time with only O of n plus m extra space? Yes. Oh wait. N plus m. That's a little harder. Let's think about this for a minute. So, one idea is to just simulate which one can do, but odd valued cells. Okay. So excuse me. Let me think for a moment here. Once an index is processed, gives the whole row and the whole column, both of those all of those become odd valued cells. They'll all become 1, except for the midpoint. So it'll be m plus n minus 1. Or minus 2, rather, actually. M plus n minus 2. Then the next iteration will potentially overlap. Actually, it necessarily overlaps. Although 0, 1, and 1, 1. If one of these indices is shared, then it actually modifies the entire row and column and flips all those bits. Well, that's interesting. Yeah, you probably... I mean, a simple way to do this is just keep track of the rows and the columns, which ones have been, like the frequency of the rows and the columns. And then excuse me. The frequencies of the rows and columns could tell me what those values should be in terms of the I guess not including the intersections, like discounting the intersections. So a particular row, if the frequency, and it just toggles back and forth, doesn't have to be exactly a frequency, it could just be a toggle. So for 0, I would see 1s across, and then for 1, I would see 1s across. However, at 0, 1, which is on that row, and at 1, 1, which is on that row, those get an extra point, don't they? Just thinking here. Any particular index is going to be think about this for a minute. Where the intersections occur in the columns. So if I could have the rows, and then I could have the columns. And yeah, the intersection points of the rows and the columns are of interest. Can't really think about this, huh? I do. Well, if it was just the rows, like I said, it could just be a toggle to tell me each row, and you would just say, well, that whole row is going to end up being either odd or even, the parity. However, when I add a column, then all the rows in that column flip. Um, so if the parity had some pattern, depending on how many rows there are, or columns there are, that pattern will flip. Do I know the pattern? I do. It's the same pattern for every column. Every column has the same pattern. It's defined by the row. By the rows, the row frequency. So I can get a column to work with out of the rows, and then I would know sort of 1010 pattern, total number of bits, and then how many of them are flipped. And then if the column number of columns flips those bits, then I would just take the inverse and add that. If they don't flip them, then I would leave it. I think that's it. I could just do a quick rundown through what the rows give me. Yeah, that's interesting. It's kind of subtle, I guess. That works. I'm trying to think how that lines up with this O of m plus n and extra memory, extra space. I would just need to save the bit pattern, and really you don't even need to save the bit pattern, but just save which parity, how many bits are flipped in the bit pattern parity. Upgrade speed for view cross multiplication easy. What's up, GGG? Howdy. What's going on, man? So I think that works. I'm gonna go for that. But yeah, they asked for. I think that's what they're looking for. O of n plus m plus indices length. O of n plus m extra space. Yeah, it should be correct. So we're gonna say m frequency. So int row frequency m. I guess we'll do it this way. Well, you could do a little bit easier. Since m and n are small, you can actually do something like this. Local frequency rows 50. We can do the same thing for frequency columns. And you just have two passes through indices, constant auto reference indices. It's actually faster to just fill these with zeros. We'll do some memset. Okay. So frequency rows, we're going to increment v of 0, frequency of columns, v of 1. And then we're going to say, it's actually not going to be frequency. It's going to be Boolean. Toggle. Going to toggle. Okay. And then we're going to go ahead and shouldn't be frequency, should be parity. I don't always refactor like that, but I probably should. It's a little bit faster. Okay. Okay. So now we would say total or pattern, constant total. So the total number of bits is going to be m. The number of rows is m. The pattern is going to be, I guess the sum over p rows. How many are true? True is going to be the, that's going to be how many are, yeah, that's going to be how many are, oh shoot, it's a mistake. Hold on a second. Sorry. So let's do columns for each column. It's going to be int I is 0, I is less than n, plus I. It's the number of columns. And for each column, we're going to say result plus equals, depending on the column pattern, it's either going to be pattern or m minus pattern. Yeah, something like this. Let's see. Okay. Int. Got it. Mem set false. Yeah. That doesn't work if he's. Mem set doesn't work anymore here. I think I could be wrong. Raw. Okay. 0 expected 6. So it's a bunch of stuff here to think about. So the pattern, it's going to be, yeah, each of the rows, I'm going to add all these parities together, and the value of true means it's an odd parity and false is even. So this is correct. And then I would say if the column's value is true, it's going to flip the parity of the pattern for the column. So this is incorrect. This is actually the way around. If it's true, it flips the pattern. If it's not, then the pattern stays the same. Flipping the pattern, basically, there's a certain m is the total number of bits that are possible, and there's a pattern of how many bits we have set based off of the rows that were toggled. And then if we just subtract that from m, then that would be the same of flipping all those bits, would be the same number of bits. So that's what's going on here. This I think is correct. But I'm missing something here. Something's not quite right. I don't know why I got 0. Oh, it's right now. Okay. I was going to say, I was like, wait a minute. Shouldn't this be correct? I'm going to go for it. I think this is right. Easy. Oh, yeah, we already said easy. We already read that. Easy peasy. There we go. That's pretty efficient. Got it. Yeah, that's what they were looking for. This n plus m plus indices length with only n plus m extra space. Yeah. I think this idea is fine. May not be the best way to do this, but this works. So we'll move on. Oh yeah, too bad. Am I still having dropping frames? Yeah, okay, but it's manageable. Dropping frames, but it's manageable. Let me see here now. I want to go to the next question. Neighboring bitwise or XOR. Okay, 0 indexed array derived with length n is derived by computing the bitwise XOR. How much time have I used so far? It's been an hour and a half. Yeah, I think I was going to go for 3 hours. Okay, computing the bitwise XOR of adjacent values in a binary array, original of length n. Okay, derived length n, bitwise XOR adjacent values. Each index I in the range 0 to n minus 1, I equals n minus 1, derived of I equals original I, XOR original 0. Otherwise, derived of I is equal to original of I, XOR original I plus 1. Okay, so it wraps around, that's what they're suggesting. Okay. Whether there exists a valid binary array original that could have formed derived, return true if such an array exists, or false otherwise. Binary arrays, only zeros and ones. Oh, interesting. Okay. Huh. No valid original array that gives derived. Oh, that's interesting. I don't know. Okay. The zeros or ones. I mean, let's see. So if the derived array is 1, then that means, oh, that's interesting. Oh, these have to be equal to each other. Okay. I think it's always true that you can get, actually it may not always be true. I'm not sure. I get the feeling that it's always true except for this like kind of special case. I could be wrong, but that's my first guess. Okay, so the 0, 1 has to give me 1. 0 XOR 1 has to give me 1, which means either this one is 1 or this one is 1. Okay. Then 1, 2 has to be a 1, so either this one is 1 here, and this is 0. probably the easiest thing to do is just select the original value as 0 and work it through and see if it works, and then select it as 1 and work it through, see if it works. And if those both don't work, then it doesn't work. So if we select the first bit as 0 here, then the next bit has to be a 1. Then the next bit, this is a 1 and a 1. That means this one has to be a 0, just this one. And then this one's 0 with the original, which I said was, we picked a 1. Oh, no. So let's say we start with 1. We start with 1 here. This has to be 0. This being 0 means this has to be 1. Say 1, 0, 1. But then you have 1 here, which gives us 0. That actually works. 1, 0, 1 also works. Yeah. 1, 0 would give you 1. And then 0, 1 gives you 1. And then 1, 1 gives you 0. Yeah, so that's fine. So you could do either. There's two solutions there. So you could do 1 or 0, and then if neither of them work, then that's it. Okay. So, let's do current. Current equals 0. Let's say constant x derived. Then we would say current is equal to x. So we're x. I kind of have to think about this a little bit. If the first value is a 1 and I selected 0, then I would 0 XOR 1 gives me the 1 for the next value. Okay. It's a 0 and I picked 0. I need a truth table. Current, derived, next, 0, 0, 1, 1, 0, 1, 0, 1. And this is going to be next is going to be 0, 1. Yeah, because I would just take current XOR derived. That gives me next. Okay. So that'll give me the next value. And you can always do this. Doesn't matter what the value of current or derived is. You're always going to get the next value. So this will basically give me the last value. Just have to check if derived out of the back is equal to zero XOR current. or just current. I think that's it. I could basically XOR, if I XOR everything straight across in derived, then all of these cancel until I get, actually if I XOR the entire thing, I'll get all zeros. I think I'd want to XOR everything until the last element. And that'll give me like original n minus 1 and n, or n minus 2 and n minus 1. I get 0, original XOR, like n minus 2. It's only when it sort of cycles back where it really matters. I want to get n minus 1 and then check that so if I just XOR everything up to, I think, n minus 1, I end up with the original x0 XOR'd with, so there'd be these two. I would get this original 0 XOR'd with original 2. And if I select the original 0 to be 0 and then XOR it, then I'll just get this original n minus 1. And then I just have to check the last element. I think that's all I need. Which actually, I only need to do this loop once. Int last, or just less than all. Okay. Let's say like accumulate, or let's do it this way. Ek. Oh, okay. All right. So now we're gonna say each of these cases. So derived back, right? XOR'd with 0. Oops, do that. Okay. So in this case, these two would give me 0 and n minus 1 XOR'd. And I would XOR this with 0, right? Assuming the original is 0 is 0, XOR that, and I get n minus 1. And then I would have to take this XOR'd with derived back, which has the 0 in it. So I would XOR the n minus 1 here, and this gives me the 0. And I would need to show that this is equal to 0. Okay. And then just do the same thing. If I XOR with 1, it's going to be equal to 1. That's it. This whole thing. A little odd, but that works. Sir, how to be good at LeetCode? I mean, what to study and from where? What's up, you day sing? Hope your day's going well. Welcome, welcome, howdy. To be good at LeetCode, give me 1 second. Let me just test some stuff. And then, give me a little more testing things. That's a good question. Interesting question. Let me check a couple other things before I answer. Yeah, okay. And let me run this, see if it works. I think this is correct. I would assume it's correct. Oh, destroyed. Absolutely destroyed. Didn't even think about it. Okay. Gulp. That's kind of a base case. I didn't even think about that. I think that's always true. How does that even? Oh, it's still wrong. Oh, it's always false. Oh no, I think it's I don't know, actually. I don't know. Hold on. Oh, that's funny. 0 XOR to 0 is 0. It's true. Yeah. I'm gonna go for it. Oh. I got wrecked, man. Okay. I should have checked that. I should have checked the size. That's a bummer. That's bad on my part, dude. Gosh. It could be size 1. I didn't even think about it. I didn't even think twice about it. Oh my goodness. Yeah, the logic I was working with assumed there were at least 2 elements. Oh, that's a bummer. It's brutal. It's brutal. It's brutal. All right, let me answer your question now. Oh, that's a rough one, dude. I got wrecked. All right, so to be good at LeetCode, more than anything else, involves practice. And this is important. You need to sleep. You need to practice. So sleep is going to help remember what you learned during your practicing. But also more than that, there's a subtle thing that happens where you don't know an answer to a question. And you probably will never know that answer to that question because some questions are not fair. And they assume that you have knowledge that took all of humanity 100 years to figure out. So they would be expecting you to have figured something out It's basically impossible to figure out as an individual in your own lifetime. And they're expecting you to have already somehow conjured up that knowledge. So for those questions, you've got to actually increase your knowledge and learn those things that they're asking about in order to answer them. So I guess the bottom line is try to find questions you don't know the answer to and look up the answer. Basically, gain a lot of knowledge. You could try to just learn lots and lots of different algorithms. You could do that too. That's another way. There are, I think, thousands. So there are a lot of patterns to learn. But basically, it's a knowledge game. So there is another element to it, but it's mostly just knowledge and pattern matching. So a lot of practice, a lot of studying, and don't waste a lot of time on something you don't know the answer to. It's kind of silly because, like I said, it's a bulk knowledge, bulk practice, bulk pattern matching thing that you need to do. It's not you're not doing R&D over here, okay? You're not coming up with brand new algorithms. While there are some questions that are ad hoc, even those have patterns that are sort of micro patterns. So what you're looking to do more than anything else is practice. And get plenty of sleep. Plenty of practice. Look up new algorithms for yourself, patterns, learn them. If you get stuck on a question, don't spend too much time on it. Try to get a hint and then learn that and move on. Yeah, obviously, I'm very familiar with bit manipulation stuff here, so I was able to come up with something. I kind of should have figured this out a little bit sooner, but yeah, that would be my advice. Lots of practice. Let me submit this one more time. When I get one wrong, which happens every now and then, I get so bummed out. Not bummed out, but I submit it like 100, several times to try to balance it out a little bit. I'm going to take one moment here. Let me just read this first. Find numbers with even number of digits. Array of numbers of integers. How many of them contain an even number of digits? Oh. Yeah, this one, there are a few things you could do here, but probably the easiest thing is just count the digits for each number, which we'll do right now. There is something subtle here. Come back to it. Yes. Even number of digits. Okay. I think this is it. There's some subtleties involved. Oh, none of them are 0. Okay. I think this works. In the 0 case, you have to be careful. You'd have to set it to 1 if it's 6 is 0. I think I'm going to go for it. Let me just test a couple things. Okay, I'm going to go for it. It's probably correct. Could be something subtle that I missed. Okay, it's correct, but look at that runtime. Wow, 1% of the solutions, huh? Oh, okay. There we go, 100%. Okay, got it. All right, we'll do the next question. Read the next question. There's not much to say about that one. There are like a lot of things you could think about or say, but that's what I did was probably the most straightforward way to do it. Operations to obtain 0 non-negative integers num1, num2. One operation will subtract the smaller from the larger. Well, I subtract the larger from the smaller. Okay, number of operations required to make either is 0. Oh, that's interesting. Excuse me. You can calculate this really efficiently. You can do this in like log time or logarithmic time really fast. So, okay. We're going to use a while loop or for loop. We're going to say int result. Ready for this? This is probably about as fast as you could do it. This is one of the it's one of the fastest. It's fast and definitely it's very fast. It's fast. Num1 is greater than 0 and num2 is greater than 0. We're gonna do constant min-val. Oh, actually, let's just do this. Then num1 minus equals, we're gonna do num1 divided by num2. Okay. And then we're going to set num1 equal to mod equals num2. Yeah. Yeah. Okay. What did I just do? Right. Yeah. I think that's it. Yeah. Let's do some larger numbers. I think this has to be some. All right, let's try some of these. Getting carried away with this here, man. I was gonna do something. I'm gonna go for it. This is probably correct. Yeah. And this also should be extremely efficient. Yeah. This is related to the Euclidean algorithm, GCDs. It's effectively calculating a GCD. It's very similar. Yeah. Yeah, that's fine. I was gonna say there's other ways to do this, but this structure but this is fine. All right, I like that question. It's a good one. Okay, number of students unable to eat lunch. The school cafeteria offers circular and square sandwiches at lunch break, referred to by numbers 0 and 1 respectively. While students stand in a queue, each student either prefers square or circular sandwiches. The number of sandwiches in the cafeteria is equal to the number of students. The sandwiches are placed in a stack. At each step, the student at the front of the queue prefers the sandwich on the top of the stack. They will take it and leave the queue. Otherwise, they will leave it and go to the queue's end. This continues until none of the Q students want to take the top sandwich or thus unable. Okay. Are we starving students today? Is that what's going on? Okay. All right. Fair enough. If I have to, you know. You are given two integer arrays, students and sandwiches, where sandwiches of I is the type of the ith sandwich in the stack, and student j is the preference of the j student initial queue. Zero is front of the queue. Return the number of students that are unable to eat. Oh my gosh. Alright. Alright. Sandwiches, students. Okay. It's only 100, alright. I think that's we just simulate. We just simulate this. Okay, that's fine. Simulation is fine. We need a queue. Yeah. Queue and a stack. They give it as a vector. The students, I think I dumped them into a queue. And the sandwiches, I guess possibly a double-ended queue, I'm not sure. Front student leaves the top sandwich and returns the end of the line, making students 1, 0, 0, 1. Where's the top of the stack of the sandwiches? I equals 0 is the top of the stack. Alright, so we'll use a backward stack. Okay. So I think I need to keep a count. Probably the easiest way to do it is use a queue and keep a count. So we can do it like the following. So int I is 0. We're gonna pop the stack, the sandwiches using I'm gonna rename this lunch. So the way this is gonna work is for loop. I'm gonna say there's a few different conditions that'll break this for loop. So come back to that. Number of students that are unable to eat. Okay. Turn queue.size. Okay. A few things. So queue is not empty. Keep going. And gonna have a size zeros and ones. And we're gonna loop through we'll keep it simple, right? Zeros and ones, and we would say, and zeros, 0, and lunch I is 0. It really should be not. Same thing here, 1's 0, lunch of I is 1. And I is less than lunch.size. Yeah, a few different conditions where this could break. If the queue is empty, then we're done. If we've eaten all the lunches, then we're done. Or if the students that can eat the lunch are all gone. And in those cases, then we're done. Okay. Now what we're going to do is we're going to say constant student q.front qpop if student is not equal to lunch of I, q.push. Okay, this probably should be STS instead of ST. Just kind of quickly. Okay, that's not good. Don't do that. Okay. And otherwise, increment I. Something like that. Something that's simple, I think. TLE. Okay. Oh, right. Zeros and ones. Okay. Forgot about that. So zeros minus equals. So student lunch of I is 0. Lunch of I is 1. There we go. I think this is correct. I'm just going to go for it. I could be wrong, but I kind of just want to try it. Yep, that's right. Okay. Yeah, I don't know. I'm just kind of looking at this question like, I think I could do this and do it quickly. The constraints are kind of small, so the simulation's not too hard, but it's not too hard to simulate. Let me look at another question. There's something I need to do. I want to read the question and take a moment. Just friendly reminder, if you like the stream, don't forget to subscribe and give it a like. I do more streams later. They're on similar sorts of streams. I'm only 2 hours in. I still have a full hour. Awesome. Count negative numbers in a sorted matrix. Given a m by n matrix grid, which is sorted in non-increasing order, both row-wise and column-wise, return the number of negative numbers in the grid. Non-increasing order, both row-wise and column-wise. Huh. I mean, I could binary search on each row to figure out how many negative numbers there were. But, O of n plus m, oh wow, okay. Yeah, you can. That's actually better. Yeah, you see, you can start in the top left corner, which is going to be the largest. And then you could basically trace out the diagonal. Or if you start in the top right corner and you find the boundary there, right to left. And then when you go down, the boundary is at the same position or further to the left. Yeah. Okay. That works too. Let's do that. Okay. 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 Um, so the column is going to be the index to the left of the leftmost or rightmost, or the first negative number left to right. First negative left to right column is going to be to the left of that. If that index is 0, that means we're adding 1. No, that's not right. If the index is 0, that means we're adding the whole row size minus 1, which is 0 plus 1. So you'd add 1 to the column, but you're subtracting it. Yeah, something like this. Let me see if this is correct. Yeah, this is probably correct. I'm just going to go for it. This is probably correct. Could be wrong, but I think it's right. It's fine. Okay, very good. 100%. Pretty good. Not too much to say there. All right. Give me a moment. Just a moment here. I was going to read. Also, yeah, I was going to read the next question. What is this? Wait. Oh, why is that happening? Whoops. Oh. Why did that do? Oh, whoopsies. I had something. I'm sorry. Jeez, my computer was doing something. I must have pressed a button or something. My computer was probably running so slow. Okay, let me deep breath here. Okay. Let's look at the next question. We'll just read it. And then I get like carried away. We'll read it and then there's something I need to do. Check if all characters have equal number of occurrences. Given a string S, return true if S is a good string or false otherwise. It's good if all the characters that appear in S have the same number of occurrences, the same frequency. Okay, so frequency map. Question. Where's your frequency map question? Oh, okay. Yeah, this is. Oh, I need to. Hold on 1 second. 1 second. All right, I'm back. Did I do this properly? I meant to close that, open it. Is it open? So frequency map questions are not the hardest. Basically, what I can do here is start with the frequency. It's pretty straightforward. And then what I can do is I basically want to say results true, return results. We're going to say all of them have to be equal to each other if they're not zero. I just need to find the first that's not zero. Int target val. This is 26, increment I. We'll just say end target string 0. Target equals frequency 5. Actually, even better than that. Let's try this. Try it this way. Logically, it's a little bit different. Okay. I was gonna do true, false. Well, it should be and, by the way, not or. It should be true initially. Okay, I'm gonna go for it. I'm pretty sure this is correct. The logic could be wrong, but there we go. Yep, it's quick and correct. All right, let's keep going. How are we doing on time? Got 2 hours and 20 minutes in. Another 40 minutes. Okay. Array of paths, paths of I, city A, city B, direct path from one A to B. Turn the destination, city without any path, outgoing to another city. Interesting. No outgoing. Okay. Forms a line without any loop. Exactly one destination city. Excuse me. So I'm looking for one of these that doesn't have any outgoing edges. Oh, these are strings though, aren't they? That's annoying. I might need to use a hash of the strings, which is really irritating. Kind of would prefer not to do that. Is there maybe an easier way? Well, it's going to be all of the... Shucks. It's not C. It's not B. Ooh. Excuse me. Thinking here. Yeah, we'll just use a hash map. It's fine. It's okay. All right, that's fine. Just say from It's something like this. I'm not so sure about this one. For some reason, it looked right when I did that. And paths. Oh, it's not paths. It's from. Wrong. Unfound should be so. That's why. Kind of typos here. Oh, still wrong. Lima. That's right here. Huh. Hmm. Oh, that's also wrong. Oh. Oh, why do I do these things, man? I don't know. I goofed. I made so many mistakes there. I think because I'm racking my brain to see if I could figure out how to do this without using a hash set and okay, it's fast enough. All right, it's fine. I guess the constraints are small enough where this works, but yeah, it's kind of awkward, this approach. It's not my favorite approach. Did get 100%, so that's pretty good. Let me see, we're doing on time. Still have, yeah, half an hour. All right, we'll keep going. Keep going. Just give this a refresh. Number of rectangles that can form the largest square. Just a quick reminder, those of you who are interested, if you like the stuff I'm doing here, give me a subscribe and a like. Don't forget to subscribe and like. Number of rectangles that can form the largest square. You're given an array of rectangles or rectangles of I. L sub I, W sub I represents the ith rectangle length L sub I and width W sub I. Excuse me. I'm getting tired now. Rectangles. Length and width, okay. Can cut the ith rectangle to form a square with a side length k, both k is less than or equal to L sub I and k is less than or equal to W sub I. Excuse me. For example, if you have a rectangle of 4, 6, you can cut it to get a square with a side length at most 4. Excuse me, max length is the side length of the largest square you can obtain from any of the given rectangles. Turn the number of rectangles that can make a square with the side of max length. Oh, okay, interesting. Should only be like, oh, I guess there's 3 of them. I was gonna say it shouldn't be that many. Okay. Oh, sure. A few ways to do this. So, fortunately, there aren't that many rectangles to work through. Yeah, this is not too bad. We're just gonna find the max length first, and then count. Like this is gonna be kind of a straightforward one. So, max length is 0, and const auto reference C rectangles. Max length is gonna be max std min v0 v1. Oops. And result 0. Std of v0 v1 is equal to max. I'm sure there are better ways to do this, but this is a very straightforward way to do it that you could program very quickly. So, and this probably is 100% in terms of speed as well. So we'll go for this one. It's close. Actually, it's kind of slow. Oh. Oh, wow. It's really slow. Okay. Huh. I wasn't expecting that. All right. Let's do, yeah, I could do this. Okay. Um, Yeah, let's try some cache locality manipulation. Okay. We'll try that and then do the same thing here. Oh, okay. Um, okay. Something like this. Wrong. Of course it is. Hmm. Hmm. Why is this wrong? Oh, probably because I need to get rid of that line. Might have something to do with it. There we go. Let's try this one, see how this goes. Still kind of slow. Gosh, man, I'm surprised. I was getting kind of tired here. Kind of sleepy. No, man, this is slow too. Okay. Why don't I just say dump of I? Um, you know what? Let's do it this way. Okay. How about that? Okay. All right, how about this? How about this? A little bit different. Oh. All right, let's try it. Slightly different approach. It's correct. Let's get slow. So slow. Ah, it's terrible. It's terrible. 23 milliseconds is kind of fast. All right, we're changing this up. Let's go back to what I had before. I had to use the dump. Go way back here. Breathe, man. Breathe, man. Breathe. Okay, hold on. This is what I had before, I think. All right. So we're just gonna say v of 0 is n. Okay. Save some operations, do it this way. Let's see how this goes. Ah. Oh, this is slower. Oh, this is slower. No, it's not much slower. It's fine. All right, I'm gonna try one more time. Let's see if I get some micro optimizations here. Yeah, it's not 100%, man. Are there better ways to do this? Maybe. Maybe. Let's see. Loop fusion to do it in a single pass. Oh, interesting. It adds a branch prediction. Yeah, actually, loop fusion is probably the way to go. For some reason, I was having a hard time thinking my way through on that one. Okay. Something like this. This might be better. Preparing for an interview. What's up, Arrow Sazi? Howdy, welcome. Not really, not exactly. Kind of a mixture of things. But I guess practicing, training my. Oh, Submitting too frequently. Okay. Training my brain, I guess. Practicing. More generally practicing. Actually, I think the two-pass solution might be faster than the, no, it's not. No, I think the best I got so far was like 20 milliseconds. It's kind of surprising. Mm. Hmm. Hmm. Merge the min calculation into the if condition. Hmm. Start to fall asleep here. Running out of steam a little bit. Into the if statement, if condition to potentially avoid a redundant min call when the value is not greater than or equal to the current max. I mean, you know what? I don't know if I need an if else statement here, by the way. I don't. Don't need that, actually. Hmm. Hmm. I don't know, man. Yeah, I don't know. It's probably about as fast as it gets. IO optimization. Hmm. I don't know if that's correct, what they just suggested. What was the, this was IO base, sequence.io. Scene time opener. We'll make this auto. red local. That's not, I don't think this actually matters. Adding a immediately invoked lambda expression. Actually, I think it's just iOS. Something like this. It's not going to be much faster though. I think that's it for this question. Yeah, the fast I/O I don't think matters that much. You can check out these solutions as well in the graph to see how they import efficiently. I appreciate that. Thank you. Yeah, I've done that a few times. Oh, it's actually a little bit faster. All right, the fastest is 18 milliseconds. They're all probably about the same thing. Oh, he did what I did. Yeah. Use 2 passes. I don't know. I'm not sure if it matters. 2 passes will be faster than loop fusion. Yeah. It's not really clear which one's better. I'm so close though. Shit. Like just 3 milliseconds. Okay. Yeah, they're pretty similar. All right. I probably just need to keep rolling until I get 18 milliseconds, basically. I think we're not gonna waste too much time on that. Okay. So I'm getting really tired though, I have to say. We're doing I got another 10 minutes, okay. Minimum number of chairs in a waiting room. You're given a string S, simulated events at each second I, S of I equals E, a person enters the waiting room and takes one of the chairs in it. S of I equals L, a person leaves the waiting room, freeing up a chair. Okay, turn the minimum number of chairs needed, select the chair. A chair is available for a person. Oh, this is a classic stack question. You don't really need a stack, but so we're gonna have int current 0, max val 0. So it's going to be const char ch s current plus equals s y equals e, current minus equals s of I l, and we're going to say max val std max val and return max val. I think it's that simple. It's pretty straightforward. Assuming we don't have to go negative. Valid sequence of entries and exits. Yeah, I was gonna say you could end up in a position where more people are leaving than are there, which happens in other test cases. Yeah, it's a pretty simple one. Okay, check if the number is a sum of powers of 3. integer n true if it's possible to represent n as the sum of distinct powers of 3, otherwise return false. Distinct powers of 3. Power of 3 exists integer x such that y is 3dx. Oh. Okay. A sum of distinct powers of 3. Huh. Well, if it's a power of 3, then you could divide by so you either subtract 1 or divide by 3. So if it's one of these cases, then you divide by 3. If it's one of these cases, you would subtract 1. Yeah. If it's ever, so that would be like 1 mod 3 or 0 mod 3. If it's ever 2 mod 3, it's return false. It's 1 mod 3, subtract 1. Although, yeah. So that's all. So 4 and it's greater than 0. True. If n mod 3 is 1. Let me see this. Else. Um, something like this. Something like this. I think it's it. Let me just go for it. There might be a more efficient way to do this, but this probably works. Yeah, it's fine. Okay, it's pretty good. That's like a logarithmic times solution, I think. Should be pretty fast. Stars from a string. Given a string S contains stars, you can choose a star in S to remove the closest non-star character to its left, as well as the star itself. Turn the string after all stars have been removed. Okay. All right. So I don't want to go right to left, I think. Okay. Closest non-star character. Okay. So you remove these two in this one. Let's get COE and LE. Yeah. Okay. We'll go right to left. I think it's the way to go. This is not too tough. Okay. So let's say stood string results. Yeah, that's this way. Okay. This way. If see, it's equals this count. That's fine. Okay. Something like this can work. Let's see. Okay, how are we doing? Sorry about that, everybody. Oof. That was a rough one, huh? By the way, if you like the stream, don't forget to subscribe and like. That was a rough one, huh? Okay, I think we're good. I think we're back. Sorry about that. Jeez, man. Oof. Oof. I run into issues every now and then. Okay, show code. So hopefully 83%. It's not the, oh yes, this is correct. It's not the most efficient, I think, but reasonable. Let me see if I can get some idea. Yeah, not perfect. Let me go one more. We'll go one more. I might need to open a new window here. I think I should. Okay. It's tricky. Critical flaw. Hmm. They're suggesting pop back, push back. Okay. Okay, fair enough. Hmm. Although it's pretty fast. It's pretty fast. It's not the best though. I'm gonna add another one of these. Okay. Oh, try again. Oh, that's not good. Hold on. There we go. All right, they're suggesting use a stack. Okay. Um. Okay. Okay. If ch is star. We're gonna solve that. Oh, it's wrong. Okay. Let's try this. This might be quicker. No. That's not faster. That's easier to program for sure. But it's not faster. No. Not quite. Not quite. I think the solution I had might have been faster. Yeah, I liked my other approach. My other approach is pretty good. It was reasonable. I think this one's faster. You sure it's less efficient? Fast seems to be a bit faster. Um, hmm. Hmm. Oh, did I? Oh, yeah. I optimized. Oh, I forgot. Right, never mind. I'd optimized this before. I didn't realize. I forgot what I did to optimize this. I optimized it slightly. Wrong answer now. Not optimized. Oh, yeah. Okay. That's confusing. No, it's just wrong. Okay. The logic is a little bit involved there. Oh boy. Okay. Hmm. Hmm. Yeah, it seems to be faster. 4 milliseconds is pretty good. All right. So ch equals star, count plus plus, not equal to star, and count is greater than 0, minus count. Try to eliminate these if statements if I can. And then not equal to star, and count is less than 0. Okay, yes. I mean, it's one way of doing things. It's one way of doing things. Okay, could try this. This is like a little wonky. I'll go for it. It's probably already optimized by the compiler, but just in case. In case I could squeeze out some, squeeze out a little bit of performance here. Still have to reverse this. Yeah, I mean, 4 milliseconds is pretty good. All right, I'm not going to spend too much time trying to get this to be 100%. It's kind of silly trying to do that, quite frankly. Let me just do one more, and then I think I'll go to the next group. I think actually I'm over time now. Yeah, I'm a little bit over time now. It's probably time for me to go to sleep, quite frankly. Let me just see. What did it say? Okay. Hmm. Hmm. Highly optimized variant. Cool. Legitimate performance optimization for cases where the output string is significantly smaller than the input. Interesting. Huh. I'm not sure. I don't know. Seems okay, I guess. Let me stop here. I think I'll read the next question, then I'll stop. I think I spend too much time trying to like fully optimize. Excuse me, yeah, I do. I spend too much time trying to fully optimize. It's true. Okay. Flip square submatrix vertically. 3 integers x, y, and k represent the row and column indices on the top left corner. Row and column indices on the top left corner of a square submatrix, and the integer k represents the size of the square matrix. Oh, okay. Flip the submatrix by reversing the order of its rows vertically. Order of its okay. Reverse the order of the rows. Return the updated matrix. Interesting. Okay. So unfortunately, if it's kind of tricky. Yeah, it's not the easiest thing. Yeah, I mean you could write a column reverse routine. It just does the swaps. And then just do it on every column. Yeah, that's fine. That's fine. Okay. That's not too hard. I'm gonna pass on this one though. I'm very tired. It's time for me to sleep. Made some progress today, but yeah, again, if you like the stream, don't forget to subscribe and like. Thank you all again for watching. I'm really tired. It's time to sleep. Yeah, take care. I may or may not stream later tomorrow. We'll see. Yeah, we'll see what I'm doing.